Assalamu alaikum. Today, in this class of Standard 9, we will solve questions of exercise 6.2 and we'll begin from question number 2 of this exercise, because in the previous lecture we discussed two theorems of this exercise and solved question number 1 of the exercise. Well, before we begin the question, let us quickly go through the statements of the two theorems we did last time. These are two very important results. You'll have to use these frequently in the coming days and the years that will follow. The first theorem states that in an isosceles triangle, means the triangle which has two sides of equal length, such a triangle is called an isosceles triangle. In such a triangle, angles opposite to equal sides of the triangle are equal. We have proved it last time. And then the second theorem is the converse of this theorem, which states that if two angles of a triangle are equal, then the sides opposite to them are also equal. We have proved these two results last time. Diagrammatically, these two results can be shown like this. Consider the triangle ABC, which is an isosceles triangle with the side AB equal to the side AC. Two sides are of equal length. Now these sides have been shown by two short lines on the sides. Then according to the statement, their opposite angles are equal. Now you can see in the figure, the angle opposite to the side AB is angle C, and the side opposite to the angle opposite to the side AC is angle B. Therefore, according to this theorem, if AB is equal to AC, then angle C is equal to angle B. Two sides are equal, their opposite angles are equal. The converse of this can be shown diagrammatically. Here, again we choose a triangle. For example, this time triangle PQR, such that two angles are equal. Let us consider angle Q is equal to angle R. Well, these equal angles have been shown in the diagram by drawing one arc on each of these. And now the result says that their opposite sides will be equal. Let us find from the figure the sides opposite to these angles. Angle Q and angle R. The side opposite to angle Q is PR. And the side opposite to angle R is PQ. Thus, the result can be written as, if angle Q is equal to angle R, then PR, the side opposite to angle Q, is equal to PQ, the side opposite to angle R. Well, these were the theorems we have proved last time. Now, let us begin question number 2 of the exercise. I hope all of you have the copy, pencil, pen, and the textbook in front of you. The diagram of the question is drawn on your textbook. And I shall read the statement of the question. It is, in triangle ABC, AD is the perpendicular bisector of BC. Show that triangle ABC is an isosceles triangle in which AB is equal to AC. All of you draw this diagram, the diagram that you have on the textbook on your copy. The name of the triangle as per the statement is ABC, and it is given that AD is the perpendicular. Not only perpendicular, it is perpendicular bisector. Means it makes an angle of 90 degree as well as bisects the side BC. What does bisector mean? You know, it divides the line segment into two equal parts. In the figure, the parts formed are BD and CD. Therefore, BD will be equal to CD. We'll show these by same mark. Two short lines will be drawn to show they are equal. Well, with this information given to us, we have to show that triangle ABC is an isosceles triangle. AB we have to show is equal to AC. Well, as explained earlier in the previous chapter on geometry, as well as in the previous exercise, you have to first write the information given as well as required from the statement. Under the titles, we write first given information, and then we write what we have to prove or find. You were told earlier from the statement how you can get what is the given information, where from you have to begin, where you have to end, and then likewise what is to be proved or to be found, where from that begins, where that ends. It has already been communicated, told to you. For this question, what is given to us? Look at your textbook. The given information is, in triangle ABC, AD is the perpendicular bisector of BC. This is the given information. So you'll write that accordingly with the title given. It will be followed by to prove here, because you have to show something, some results to be proved. The result to be proved here is triangle ABC is an isosceles triangle. You have to show two sides of this triangle are equal. The side AB is equal to the side AC. You have to prove this. And then after that, we prove this result. We write the title proof for it. Let us prove. Well, look at the figure. We find the given triangle ABC has been divided into two parts by drawing AD as per the statement. Perpendicular bisector of BC. It is divided into two parts. Two triangles it is divided into. You can identify the triangles. You can name them. The first one is triangle ABD and the second one is triangle ACD. Let us, to understand it easily, draw these roughly in our rough part of the copy. This is the first triangle, triangle ABD, and then second triangle is ACD. Rough figures. To get the result, we will prove these two triangles are congruent. And the congruency rule that we can use will be the one which has already been proved. Few congruency rules we have discussed earlier. We have proved one of them, and two of the congruency rules we have not yet proved. Therefore, the ones which we have not proved so far will not be used in proving this congruency. We have proved one theorem, and then earlier, before that, we have discussed one axiom also. SAS axiom we have discussed and then proved angle side angle called ASA theorem. One out of these rules, SAS or ASA, will be used for the congruency of these two triangles. To understand which out of those will be applicable, let us find from the given information, known information, which elements of the two triangles are equal. You must have reasons for those to be equal. Without reasons, we cannot choose. And as you look at the two figures, we find one of the sides in the two triangles is common. And you can easily find from the figures the common side is AD. This is the common side in the two triangles. AD completely is involved in both the triangles. So therefore we'll be using this as one of the elements for proving congruency. We also know that AD is perpendicular to BC. Therefore, angle ADB as well as angle ADC will be 90 degrees and thus equal. This will be the second point we shall use for proving them congruent. We have the reason for it. For the first one, we have reason that they are common. AD is common side. For this angle ADB and angle ADC, we have reason because it is given to us that AD is perpendicular to BC. And then we also have BD equal to CD. This also is given to us. Because this AD is not only the perpendicular on BC, it also bisects BC. It is given to us. So we have reasons. Reasons for these three elements of one triangle being equal to the corresponding elements of another triangle. So we can conclude, therefore, the two triangles are congruent. And accordingly, you can decide the congruency rule also used. We have two sides of one triangle and the included angle. BD side, AD side, and the included side angle D from first triangle equal to the two sides CD and AD and their included angle. The congruency rule, therefore, is SAS. SAS congruency rule, which is an axiom. Now, knowing the two triangles are congruent, then we conclude, according to CPCT, that the remaining elements of first triangle will also be equal to the corresponding elements of another triangle. One such pair of elements is AB and AC. AB from first triangle, AC from second triangle. Thus, we'll conclude that AB is equal to AC. Besides AB equal to AC, we will have two pairs of angles also equal. But that will not help us in this question. We need to show only the two triangles are congruent. We need to show that triangle ABC is an isosceles triangle. That result we'll get by using only one CPCT result, that is AB equal to AC. Now, knowing the two sides are equal, we'll conclude the triangle is an isosceles triangle. This is the proof. Now, let us write this proof. You can begin. We'll consider the two triangles. So, note down in triangle ABD and triangle ACD. We have AD is equal to AD. This is the common side. You can write in the bracket. Common side. Second point, angle ADB is equal to angle ADC. The reason for this we will write each 90 degrees. The reason for the first point is common side. The reason for the second point is each 90 degrees. And then third point is BD is equal to CD. The reason for this is given. It is given to us. AD bisects BC. We'll conclude, therefore, that triangle ABD is congruent to triangle ACD, and write the congruency rule used in the bracket, SAS congruency rule. And finally conclude, therefore, AB is equal to AC. The reason for this we will write CPCT. Hence, triangle ABC is an isosceles triangle. That completes the proof of this question. Over to question number 3. Yes, quickly you can draw the diagram of this question from the textbook. We again have an isosceles triangle ABC. You can draw. It is an isosceles triangle in which altitudes BE and CF are drawn to equal sides AC and AB. We know here side AB is equal to AC. Two sides are equal. It is an isosceles triangle. To these equal sides, altitudes are drawn. The names of the altitudes are given in the statement B, E and CF. B is the altitude drawn from B to AC side. CF is the altitude drawn from C to AB side. B, E and CF are the two altitudes drawn to the equal sides AC and AB respectively. We have to show that these altitudes are equal. Altitude BE we have to show is equal to altitude CF. And if you have drawn the diagram, let us analyze the statement again and find what is given information, what is required information, and write that accordingly as given part and to prove. The given, as usual, will begin from ABC is an isosceles triangle and it will end at the word respectively, after the word respectively. So the given in this statement is ABC is an isosceles triangle in which altitudes BE and CF are drawn to equal sides AC and AB respectively. Now this will be followed by what is to be proved. You can see from the statement we need to prove that these altitudes are equal. BE we have to show is equal to CF. Let us prove this. This is the proof for this. Well, as I said in the previous question and earlier also, to prove this question, we would like to make things simple. We'll choose two triangles which will help us to prove the result. And when we look at the given figure, since we have to prove BE is equal to CF and we know AB is equal to AC, therefore the two triangles that we'll choose must involve both these informations, given information as well as the required information. And when we analyze, when we look at the figure, we find out of these AB and BE are involved in this part of the figure. It is triangle ABE which is formed here. In this we have angle at point E equal to 90 degrees, we know it. And correspondingly, the second figure, second triangle, which involves the side AC and CF, is this one. These are the rough figures and will help us to prove this conveniently. These two figures, these two triangles from the given figure we shall use to get the result. In this second figure also we have angle F equal to 90 degrees. So I marked it by using a symbol for 90 degree angle. To get the result, you have to prove these two triangles are congruent as we did in the previous case. The information that we have to prove this, we know AB is equal to AC. This will be one of the points we'll be using to prove the two triangles are congruent. AB equal to AC, we know it, it is given to us. Then we also have this angle at E point, vertex, equal to angle at F vertex, each 90 degrees. This we'll use as the second point for proving these two triangles congruent. And if you look at the figures, you will find some more information which will help us to conclude the two triangles are congruent. We need third point also, third result also. And the result is we have a common angle in the two triangles. Angle A is common in the two triangles. You can see the main figure. Angle A, at vertex A there is only one angle formed. If you look at all other vertices, at each of those vertices more than one angles are formed. But this is the only point here where only one angle is formed, and this vertex is completely involved in both the triangles. Therefore, the angle which is formed at this vertex belongs to both the triangles and will be therefore called as common angle. Thus, the two triangles now we can conclude are congruent because we have two angles of one triangle equal to two angles of another triangle and one side of the first triangle equal to the corresponding side of another triangle. Look carefully, the side involved is not the included angle here. Included side here. It is not the side included by the two angles involved. If you examine in this figure that I have pointed to, the included side is AE. But we have chosen the side AB here. It is given to us. Equal to the side AC. Therefore, it does not refer to the theorem ASA theorem because the side is not the included side. Had it been included side, then we would write ASA, S between two A's. But it is not included, it is one of the sides, remaining sides. And in the second figure, we have the corresponding side. AB corresponds to AC side. Therefore, the rule used will be AAS. We have earlier discussed it. It is the corollary of this theorem, AAS theorem. Now, having proved these two triangles are congruent by this rule, we'll conclude by CPCT that BE side will be equal to CF side. That will be the result required. Now, having explained this, let us write the proof for this. We'll begin with considering the two triangles as in the previous question. In triangle ABE and triangle ACF, we have, write in the sequence the 3 points, AAS congruency rule to be used. So we'll first write angle, then another angle, then the side. Angle A is equal to angle A. The reason for this is common angle. Angle AEB is equal to angle AFC, each 90 degrees. Well, this has already been told. In the first case, we wrote just one alphabet. But in the second case, I did not write one alphabet, I wrote 3 alphabets. The reason you know, at point A, only one angle is formed in the figure. Therefore, we can give the short name. But at point E and F, many angles are formed. Therefore, if you give the short name, it will be confusing which out of the angles formed there we have included. That is why full name is given. Angle AEB is equal to angle AFC, and the third point is AB is equal to AC. It is given to us. We'll conclude, therefore, triangle ABE is congruent to triangle ACF AAS congruency rule. AAS congruency rule. And then conclude by CPCT that BE is equal to CF CPCT. That completes the proof of this question. Next we have question number 4. Again, draw the diagram quickly from the textbook. This question number 4 is the converse of question number 3. In this we have again a triangle. You can see from the textbook the information that is given to us. ABC is the triangle. This time it is not given that it is an isosceles triangle. Two sides are equal. It is not given to us. We have to prove that two sides of this triangle are equal. Isosceles triangle. Instead, what is given? Again, like previous question, altitudes are given. BE is perpendicular to AC. CF is perpendicular to AB. It is also given that this BE is equal to CF. It is given to us. BE is equal to CF. It is given. What was to be proved in the previous question is given here. Then you have to prove that this triangle is an isosceles triangle. Two things are to be proved. Number one is triangles are congruent, ABE and ACF. AB is equal to AC. Triangle is isosceles triangle. This was given to us in the previous question. That is why we call this as converse question. What was given in the previous question is to be proved here. What was to be proved in the previous question is given here. They are converses of each other. And the proof will be similar. Like previous question, will again choose the two triangles ABE, rough diagrams. We know angle at E is 90, and triangle ACF angle at F is 90. Altitudes are there. Triangle is formed, angle of 90 degrees formed. We also know BE is equal to CF. This is the second information. And then like previous question, we also know angle A is equal to angle A being a common angle. I did explain previously also. Angle A is common angle. Therefore, three elements of first triangle are again equal to three elements, corresponding elements of another triangle. Fulfilling again the criteria AAS, two angles and one side of one triangle equal to corresponding angles and corresponding side of another triangle. Is again the corollary AAS. Corollary of ASA theorem. We'll conclude by proving these two triangles congruent, that AB is equal to AC. With that, the proof of this will come to end. Now quickly let us write this. Given and to prove you can write from the statement. Let us write the proof. We have to take the two triangles. In triangle ABE and triangle ACF, we have angle A is equal to angle A, common angle. Angle AEB is equal to angle AFC, each 90 degrees. Previously we wrote AB equal to AC, but this time you have to write BE is equal to CF. This is the only change given. Therefore, triangle ABE is congruent to triangle ACF, ASA, congruency rule. Therefore, AB is equal to AC. Therefore, triangle ABC is an isosceles triangle. That completes question 4. Now over to question 5. In the meantime, you draw the diagram of question 5. It is drawn on the textbook. Copy it. Question 5. According to the statement, two isosceles triangles ABC and DBC on the same base BC. We have AB equal to AC, BD equal to CD. It is given to us. The two triangles are isosceles. Two triangles of first triangle are equal. Two sides of first triangle are equal. Two sides of second triangle are equal. We are asked to prove that angle ABD, this is the angle ABD, is equal to angle ACD. We have to prove this result. Well, as usual, given and to prove, you can write from the statement. We will go to the proof part of this. The question can be proved in number of ways. But since we are doing exercise based on the two theorems I referred to in the beginning of the class, the theorems which we have proved last time, therefore we'll use those theorems to prove this result. So there are many other ways of proving. The simple procedure will be, as per this theorem, we'll consider the two triangles one by one. I shall draw the rough diagram. This is the first triangle, triangle ABC, with AB equal to AC. Therefore, you can easily understand the theorem that we can use will be equal sides of a triangle have equal angles opposite to them. And the opposite angles here are angle ACB. This is the angle opposite to AB side. And the angle opposite to AC side will be angle ABC. Well, as I earlier said, we'll not give the short names because in actual figure both at B as well as C, many angles are formed. To avoid confusion, we shall therefore give the full name. We'll then also take the second triangle. Triangle BCD is the name. It has BD equal to CD. And then again same result will be applied. Their opposite angles will be equal. And from the figure you can understand, you can find which are the opposite angles. Angle opposite to BD is angle C. The full name we shall write angle BCD. And the angle opposite to side CD is angle at vertex B. After using this result twice in the two triangles, we'll add the two results. Addition of the results will give us the final result. Let us write it quickly. We have triangle ABC. We have in triangle ABC, AB is equal to AC. It is given to us, right in the bracket, given. And then the result, therefore, angle ACB is equal to angle ABC. The reason for this is the statement of that theorem. Equal angles of a triangle, equal sides of a triangle have equal angles opposite to them. You can write that here. Equal sides of a triangle have equal angles opposite to them. Then we'll choose another triangle. In triangle BCD, we have same steps, names will change. This time BD is equal to CD. Again it is given to us. This step, followed by the result, theorem. Therefore their opposite angles will be equal. Angle opposite to BD, we have angle BCD is equal to angle DBC. The result is same that you wrote, the statement that you wrote earlier. You can write that also here. And then adding the two results. By adding, we get. Well, as you add, you will add LHS to LHS, RHS to RHS. Left hand sides are angle ACB. This will add to angle BCD. LHS of second result is equal to angle ABC, RHS of first result, plus angle DBC. Therefore, now when you add these, the vertices in both angles on the left hand side is C. You have to add the angles formed at vertex C in the figure. ACB you have to add to angle DCB. Together they make a larger angle, angle ACD. So therefore the sum of these will be angle ACD is equal to angle. In a similar way, the vertices on the right hand side in the two angles, we have angle B. B is the vertex. And when you add the two angles at vertex B, a larger angle again is formed. The name of that angle is angle ABD. That completes the proof of this question. That was question number 5. With that, we conclude the day. remaining questions we'll be doing next time. Go through these questions, solutions, and in case any doubt is there, if you have any doubt, you can call me and ask about that later. First you go through them, and then later we can discuss the doubts about these.